Well, thanks for joining me. We're going to talk about the concept of half-life today. Now, this does not mean, early in life, you're a newborn, and then when you're, 54 years old, half your life has been, over, and then you become elderly late in life, and then your life is done. That's not what I mean when I say half-life. Half-life has to do with how long it takes a radioactive material for half of the material to transmutate or change into another material. So let me give you some examples here. If we start with a 20-gram sample and we wait for it to decay so that the pink stuff, that's what I'm going to call it, the pink stuff, goes down to 10 grams. Let's try this one more time. The animation didn't work particularly well there. So that 20 grams should go down to 10 grams. And that will be the time it takes for one half-life. Okay, whatever that is. Now, if I wait a second half-life, some people might think, well, it's all going to be gone because you lost 10 grams in the first half-life, so the second half-life is also 10 grams. No, the definition of half-life is the time it takes for half of the radioactive substance to disappear. So after two half-lives, it will go from 10 grams down to 5 grams of the pink stuff. Now, also important, and I haven't mentioned it, notice that the total mass is going to remain at 20 grams. So you'll get 10 grams of pink stuff and 10 grams of blue stuff. And then after two half-lives, you'll have 5 grams of pink and 15 of blue. And if we wait a third half-life, it will drop down to 2.5 grams of pink and 17.5 of blue, and so on. Generally, after 7 to 8 half-lives, we say that all of the original material is gone. There's always a little bit left, but not enough to worry about or measure. So let's do an example of this. So if I have iodine 131 and I start with 1 milligram of it, assuming its half-life is 8 days, after 8 days this is going to, I'll be left with 0.5 milligrams of the iodine 131. Now, what it actually broke into was xenon 131. If I wait another 8 days, so that's two half-lives, I'll be down to a mere 0.25 milligrams of the iodine 131, and I'll have 0.75 grams of the iodine 131. Now here's an important one. The next data point is not 32.08 days. Each time, notice I add 8 days. I add 8 days. So if I add 8 more days, it's at 24 days is the third half-life. And this drops down to 0.125 milligrams. In actuality, this particular reaction is a little bit more complicated. The iodine 131 does emit beta particles to turn into xenon 131, but then they also break down and make other stuff. So it's a little bit more complicated, but the general idea of you get half of the material each time remaining is the one you want to know, and that the total mass remains the same. It's not like it's lost. It does turn into another substance. I'm writing down here the equation so you can see if iodine 131 emits a beta particle and it also emits gamma rays, you're going to be left with xenon 131. So remember, a gamma is a 0, 0. It never really balances into the equation. So on the top, 131 is equal to 131 plus 0. On the bottom, 53 is equal to 54 plus negative 1. So sure enough, that balances as well. We can look at this, and we're going to look at it graphically this time. If you start with 100% of a radioactive isotope, after one half-life, that will drop to 50%. After two half-lives, it'll be 25%. After three half-lives, 12.5%, and it just keeps dropping. Now, it turns out that this line won't ever actually, the blue line won't touch the black line at the bottom, but it'll get very, very, very close, won't it? And we can visually think of this. Maybe I start with 16 radioactive isotopes, atoms of that. After one half-life, I'd be left with 8. After 2, 4. After 3, 2. After 4, 1. At that point, I would actually lose them, but you're generally not starting with just a mere 16 atoms of something. Let's go ahead and plot this. So now I'm looking at iodine 131. Initially, I have 20 grams of it. its half-life is told to be 8 days. So after 8 days, I can anticipate there'll be 10 grams of iodine 131 left. And I could graph that. So there's my 8 days. I'll go ahead and put on there my amount of 10 grams. And then I could, you see, continue this. Another 8 days would be 16 days out. I'd be down to 5. Add another 8 days. I'm 24 days. I'm down to 2.5. Add another 8 days to 32, 1.25, and so on and so on and so on. This is how half-life works. There's nothing we can do to speed it up or slow it down. It's an inherent property of that particular isotope. Now, some isotopes are pretty stable, others are not. Carbon-14 has a half-life of about 5,700 years. Potassium-40 is on the order of, its half-life is in billions of years, so we'd say it's pretty darn stable. If I take radon-222, its half-life is a mere 3.8 days, very unstable. Radium-226 is 1,600 years, thorium-230, 75,000 years, thorium-234, just 24 days. So the difference of 4 neutron makes its half-life go from 75,000 years to 24 days. Uranium-235, 7 times 10 to the 8th years, right? That's like 700 million years. Yet uranium-238, now we go to billions of years, right? So it's interesting how just a few neutrons makes that much of a difference in the stability of an atom, or at least I find that interesting. Now, I'm going to finally define for you the half-life, the time required for half of the atoms of a radioactive nuclide to decay. Now, based on that, the shorter the half-life, the less stable that nuclide must be. So I've got here a little nuclear clock, right? So initially I have 100% of my material. After one half-life has passed, half of the red is now gone, and it's changed into other stuff. After 2 half-lives, half of that red is gone. After 3, half of that's gone. After 4, and so on. So you can start to see visually what that means. Now, it turns out that potassium breaks into argon, but then argon then further breaks down into calcium. That's the reason we got all the multiple colors showing up on that slide. Another way you can figure out how much you have is initially you have 100%. Then you have half. Then you have half of a half. Well, 1/2 times 1/2 is 1/4. And then you have half of a fourth is 1/8, or 1/2 times 1/2 times 1/2, and so on. So the half-life, there's your definition of it again. And we mentioned that if you have a very short half-life, it's not a very stable isotope. So we can look at it here. The blue one is the one that's disappearing, so the surviving parent isotopes are going down, but they're producing or accumulating daughter isotopes. That's the new thing that it produces. So after one half-life, you have half of the original atoms remain of the parent. After 2 half-lives, you have half times half, or 1/2, 1/2 squared, 1/4 of the material remains. After 3 half-lives, as you might guess, 1/2 cubed is 1/8. After 4, 1/2 to the 4th, 1/16. After 5, 1/2 to the 5th, 1/32. After 6, 1/64. You can see very quickly, if you go out 7 or 8 half-lives, you really don't have anything left. All right. Let's keep looking here. I know I'm showing you the same stuff over and over again, trying to explain it. I'm not going to worry about how we do this analysis. I'm not going to ask you about that, so I'm going to skip that slide. Let's try this problem here. It involves you doing maybe a little bit of math. So the iodine 131 nuclide has a half-life of 8 days. If you originally have 625 grams of it, after 2 months, about how much will you have? Now, I know in math class, they probably, depending on which math class you're in, they may teach you a formula to do this. And I don't have a problem if you use the formula. but I'm going to suggest that you make a data table instead, because the data table, you will understand what's going on. The math formula, you'll just plug it in, get a number, and you won't really have a good sense if it's a reasonable answer or not. So here's how you make the data table. Start by writing the approximate amount, the time, and the number of half-lives that have passed. So I started with 625 grams. Then, on my calculator, I just divide that by 2, divide by 2, divide by 2, divide by 2, divide by 2. And notice these are approximate, okay? Because the question says, after 2 months, how much will you have approximately? So I didn't worry about all the decimals. I'm just kind of spitballing here, getting the best average I can. Now, after 0 days, because you started with 625, then I've added 8 days, 8 days, 8 days, 8 days. I add 8 days each time. And I went out for what I would consider 2 months, right? Because it says 2 months, and there's approximately 30 days in a month. So by going by eighths, there's no month that has more than 36 days. There's none that have 36. So I've gone far enough. So the question is, how much will remain? Well, if I'm looking at this, I would say 2 months is about 60 days. So somewhere between 5 and 2.5, or somewhere between 2.5 and 5, if I were guessing, I would write, I don't know, 3 grams would be my best guess. This is how many half-lives have passed, in case we're wondering. Okay? So my answer would be that, if I got 60 days in a month, 8 days, I need 7.5 half-lives, and it puts it right in that range here. Okay? And that's the method I would think you can use, and it's going to work for every problem we do. Okay? Now, if those are your choices, I would say 5 grams is the best answer, isn't it? So you must have had 2 28-day months in a row, because it's not going to be 10 grams, and it's not going to be less than 1. Now, if you're a math person and you want a formula, here you go. N equals n sub naught times 1/2 to the nth power. Now let me define this for you. N is the amount remaining. N sub O is the original amount that you have. And little n is how many half-lives have passed. So, if I want to plug this into my calculator, the original amount was 625 grams. And based on the assumption that there are 30 days in a month, and the half-life is 8 days, 7.5 half-lives passed. So if you take 1/2 and raise it to the power of 7.5 and multiply by 625, you get an answer of 3.45 grams, which is probably the correct answer. Okay? The problem, again, that I have with this formula is if you type something wrong and you got an answer of, it doesn't even matter. You could have got an answer of 0.108 grams. You have no basis, is that correct or not? So I would prefer that you stick with the data table method, but again, if you want to do the formula method, you go right ahead and do that. Let's try this question here. Given that the half-life of carbon-14 is approximately 5,730 years, consider a sample of fossilized wood that, when alive, would have contained 24 grams of carbon-14. It now has only 1.5 grams. How old is the sample? Now see, the reason this works is when you're alive, you're eating food. You're putting carbon in your body, and a small percentage of that is carbon-14. It's a pretty safe bet that when you die, you stop eating and you stop adding carbon-14 to your body. And that's why this principle of radioactive carbon dating works. So I'm going to try the data table method, and look what we do here. We're going to set amount, time, and half-life. Now, I'm going to start with 24 grams. Cut it in half, go to 12. Cut that in half, go to 6. Cut that in half, go to 3. Cut it in half. I'm going to stop at 1.5 because it says it now contains 1.5 grams. Now, here's the mistake students make. They put the initial time as 5,730 years. That's incorrect. At time 0, when no half-lives have passed, you have 24 grams. After 1 half-life, or 5,730 years, you have 12 grams. And then from this point, I add 5,730, add another 5,730, add another 5,730. So I'm going to suggest that that piece of wood is about 22,920 years old, right? About 23,000 years old. And that's what I would pick as my answer. Now, if you want a formula for this, it's a little bit trickier. It says natural log of n over n sub naught equal the opposite of kt. Whoa, this is looking like a lot more work than that table method. Now, the half-life of something is equal to the natural log of 2 over k. That's how it's defined. Now, if you take the natural log of 2 on your calculator, you get the number 0.693. That's what it is. Now, from here, we were told the half-life of this is 5,730 years. So I say that equals 0.693 over k. Solve for k by multiplying both sides by k, dividing both sides by 5730, and I get k to be 1.209 times 10 to the negative fourth. Now I know the value of k. Now we're going to plug into the equation. The original amount is 24 grams. The ending amount is 1.5. I know the value of k. I can now calculate the amount of time that has passed. So I have to say 1.5 divided by 24, take the natural log of that, divide by negative 1.209 times 10 to the negative fourth, and look, I get pretty much exactly the same answer. Now, I didn't make this one overly difficult. That's how you do the math. Isn't the table method looking better every second? Okay, that's really the way I would like you to do it. All right, let's keep looking here if we got any more for you to do. I've got some here, and feel free to work those if you want. And then what I'll do is I'll give you what the answers should be if you get those, and then we can talk about those in class if you have a particular question, if you don't get the answer to one of those. All right, at this point we're almost done. Let's maybe go through another little example here. I think this is one you can kind of look at. It says the half-life is this. If you originally have 3.36 grams, how much is present after 22,000 years? Well, you can do this one several ways, right? If the half-life is 5730 and 22,920 years pass, if you divide that by 5730, that's 4 half-lives. So basically you have to say number of half-lives times the half-life equal to age. 4 half-lives times 5730, well, that makes it 23,000 years old, right? And then we could go back and calculate what we're trying to find. If a sample originally contained this, how much is present now? So I'm going to have to divide that, aren't I? 4 times in half, right? So maybe the data table method will work for this. So I start with my 3.36 grams, and then I cut that amount in half. That's 1 half-life. Cut that in half. That's a second half-life, a third, a fourth half-life. If I wanted to, I can add the 5730 each time to show the 23,000. So the answer to this question is 0.21 grams. And that is where we're going to stop for today. Hopefully you have a little better idea of half-life. We'll work a little bit more on it in class. I'll give you a homework sheet with it for practice, and then I think you'll feel very comfortable with the idea of half-life. Thanks for joining me. Thanks for keeping up in chemistry. Have a great day. Bye-bye.